All right, well, good afternoon, grade 12s. We're just on our little march to finish the course, and today we're going to talk about the Compton effect, so I'm going to get right into it. I like to start with a little summary, so the summary so far goes like this. So far we've seen in the last unit that the ways that light behaves like a wave. So there's interference, there's refraction, there's diffraction, okay? There's how it propagates through a vacuum and so on. Okay, and we have the electromagnetic wave model, which, like I said, is the theory that really changed the world and created a boom in technology that we definitely feel today with our electric cars and our transformers and our motors and everything else that we use. Okay, cell phone technology, radio technology, Wi-Fi, and so on. You can draw a line straight to that theory. But now we've seen in the quantum unit how this theory fails. Okay, now it fails to explain how matter, atoms, absorb light. That's in the photoelectric effect. Also how atoms emit light, okay, in black body radiation. And we've seen that in order to fix it, and we can't really fix the wave model, what we have to do is throw it out in order to explain what's happening there. So we come up with this particle model, and the particle model explains things nicely. Okay, the photon model, the quantum model. Now, there's more. Okay, so now let's talk about this. So far we've seen black body radiation, and we've seen the photoelectric effect, and we've seen how those both represent catastrophic failures for the wave theory. Well, there's another one. Okay, it's called the Compton effect, and the Compton effect is kind of cool. It's an example of what happens. Let me explain the experiment at first. Okay, so what you do is it's kind of like the photoelectric effect, right? Although Compton did not sort of build on Einstein's work, he was sort of working on his own. So it's kind of like the photoelectric effect. They use X-rays this time, okay? So an X-ray will hit an electron and knock it out. We call it the recoil electron. Einstein would have called it the photoelectron, right? Now here's the interesting thing about the Compton effect. When you use X-rays, there's a residual photon, okay, a residual particle of light that gets scattered away, okay? Now what this shows is kind of weird. Now notice how they draw the photons. They draw them like they're a little bundle of waves. That's not what they really look like, okay? That's just a visualization. But here's the weird thing. There's an incident X-ray that comes in here and strikes this, okay? And then you get this scattering effect where the electron goes this way and a scattered bit of light of lower energy goes the other way. So this has a longer wavelength, okay? Now here's the deal. The wave theory predicts that at low intensities you could never get a change in the wavelength of light. Like, okay, let's put it another way, okay? Let's say you had waves, okay, that are shining, not waves, but water waves, let's say, that are hitting like obstacles in the water, okay, boats and stuff like that. Well, any reflection or sort of scattering of those waves, the wavelengths would be preserved, okay, if that makes sense to you. So in other words, if you have like distance between crests, sure, if they bounce off a boat, maybe they're going to lose some intensity, there's some waste heat in the interaction and everything, but the waves bouncing off will not change in wavelength. But that's what happens here. The wavelength changes. And the wave theory states very clearly that that can't happen, okay? Now, you see, if a particle hits the electron, it will lose energy when it reflects. And the energy in the photon is manifested by their color. So you get a color change, okay? So in other words, the X-ray comes in, and X-ray is a type of radiation you can't see, and the X-ray that bounces off here has a slightly longer wavelength and therefore lower energy. So that little bit of light that bounces off has lost some energy, and it's a slightly different color. I know you can't see it, so X-ray is not a real color that you can see, but you get it, right? Like let's say a violet light went in and it came out a little bluish, right? So in other words, it changed its color on the reflection because it lost some energy, okay, in the process. So that's what's happening here. Now there's something else that this shows. Remember when you're playing pool on a pool table, okay? And a ball comes in and strikes a different colored ball here, let's say like this, okay? And one ball goes off this way, and then this ball goes off this way, let's say. Whoops. I'll use black to represent the black ball. Goes off this way, and then we did these problems, right? Normally right now I'd be studying for the exam, you'd be reviewing this material, but we did these two-dimensional conservation of momentum problems. Here I'll use their same notation, phi and theta, okay? Yeah, we did here, this is V1, let's say this is M1, this is M2, whatever we want to call them. That's V1 prime, and this would be V2 prime, right? Like we did these diagrams. Well, this diagram looks exactly like that, okay? And here's the thing. It proves that not only is light behaving like a particle in the sense of the scattering and the changing of wavelength, but also there's momentum being exchanged here. Okay, so conservation of momentum applies. So it proves that these particles of light actually have real momentum, like a real particle with mass would have. So it's really behaving like a particle here, just like a collision between particles. So this looks like a collision between particles, right? And that means the electron, or the photon, pardon me, of light, this little particle of light, actually seems to behave as if it has mass. Because remember, to have momentum, you have to have mass. Now, how can a particle of light actually have mass? Newton thought they had mass. But here's the deal. They don't actually have any real mass. But we can go to Einstein for some inspiration here, okay? And we'll get to that in a moment. Okay, so anyway, long story short, I wrote out in here, Compton found something like collision was taking place where momentum was being conserved. So this is therefore particle-like behavior. Again, the wave theory fails to predict this. This is not how waves would collide with an electron. Like say, picture waves colliding with a boat. It would look nothing like that, okay? You would not get this conservation of momentum thing going on, okay? And you would not get that change in wavelength going on, okay? So again, you can explain this using Planck's idea of the light being like a particle, okay? Now, how can a photon have momentum if a particle of light has no real mass? And make no mistake, light doesn't have any real mass like you and I have mass. It's not that kind of particle. It's a particle, we call it a force-carrying particle. It's not like a physical particle like you would imagine it. It's a little particle of light, okay? But here's the deal. I'm going to show you just a little review. Remember, momentum is mass times velocity, okay? Well, if mass is zero, how can the light have any momentum? Well, Einstein has this famous equation, E is equal to mc squared. See, what a photon is energy. And energy has what we call an equivalent mass. It's not real mass, but there's an equivalent mass. So you can actually take Einstein's equation, E is equal to mc squared, solve it for m, and you get E over c squared. Now I did this for you in the notes here, just because I'm talking. Okay, you solve this for m. M would be E over c squared. See, I did it down here. Okay, and then we know that in Planck's hypothesis, we know that the energy is equal to hc over lambda for a photon's energy, right? And so putting it all together, you get this as the mass of a photon. So it varies with its wavelength. It's Planck's constant divided by the wavelength times the speed of light. Okay. Now, since all photons travel at the speed of light, so their speed is equal to c, just have to go momentum equals mass times velocity, and you ended up getting this formula here, that the momentum of a photon is equal to Planck's constant divided by its wavelength. Okay. Now, photons have very little momentum because Planck's constant is like times 10 to the negative 34. It's this really tiny number. And even though wavelengths are small, so for example, a red photon would carry very, very tiny, tiny momentum. You would not feel it, right? You don't feel a wind of light when light is hitting you. The reason why is because those photons have very close to zero momentum, but it's not quite zero, And according to Huygens wave theory, they shouldn't have any momentum at all. Like a little fluctuation electromagnetic field should not have momentum. But photons are behaving like particles. They have momentum, okay? And so it's kind of cool how that works. And this is that equation in the box is how you determine the momentum of a photon, okay? So where does this leave us? Well, we have black body radiation, we have the photoelectric effect, we have Compton scattering. Now we have three pieces of evidence. We have that the photons have momentum, okay, and that leaves us with this bizarre contradiction that the wave model that we thought was so good, okay, in the last unit, it turns out that it catastrophically fails to explain the results of these experiments. And it's catastrophic in the sense that we have to throw out the whole notion that light is a wave, okay? Actually, I'm going to do, before we move on from this, I'm going to do an example. Like here, let's do an example. Let's say your wavelength is 600 nanometers. That's our wavelength for red light. Therefore, the momentum of a red photon. Okay, I'm sorry, I gotta grab my calculator. Okay, so the momentum of a red photon would be Planck's constant, which would be 6.63 times 10 to the negative 34 divided by 600 exponent 7 negative. Pardon me. Exponent divided by 600 exponent 9 negative there. I get 1.105. 1.105 1.105 times 10 to the negative 27 kilograms times meter per second. Okay, now that might not seem like a lot, and it's definitely an extremely tiny number, but don't forget that the mass of a photon is 10 to the negative 31, like it's 9.11 times 10 to the negative 31 kilograms. So that might not be a lot of momentum for you and I, but it's enough to push around these electrons, and that's why it's significant, okay? All right, so there you go. That's the momentum of a photon. Now, if we try it with blue light, of course, we'll get like the shorter the wavelength, the more the momentum. Okay, so gamma rays would have the highest momentum, and radio waves would have the lowest momentum. In fact, radio photons are hardly ever show any visible quantum-like behavior. Okay, they basically behave like waves all the time. But the more intense the energy gets, okay, so gamma rays, basically they hardly ever behave like waves. Okay, it's kind of interesting how that works. The more energy per photon, the more the particle behaves like a particle and less like a wave. Okay, so for example, if we were to shoot gamma rays through the double slit apparatus, you'd get interference, but it'd be really hard to see it. Like the fringes would be so close together that it'd be very difficult to measure. Okay, like with the naked eye, you might not even see them. And then you conclude it's kind of acting like a particle here. See? All right, so where does that leave us, guys? And where it leaves us is with this bizarre sort of contradiction that sometimes light behaves like a wave and sometimes it doesn't, right? And what do you do with that? Like when you shine the laser through the double slit and you see the interference fringes, guys, like case closed, like that's interference. That's a wave thing, okay? If light's not a wave, it just doesn't do that. Okay, so that's one thing. That's the wave theory. So wave theory explains that, no problem. Predicts it easily, can explain it, no problem. And we can do the math and get the right answers and everything else. It all works. But if light is a wave, then the photoelectric effect shouldn't happen. And it does. And you can't explain it if light is a wave. So when atoms absorb light, light seems to change its character, right? And when you shine it through double slits, it behaves like a wave when it hits matter and absorbed or emitted by matter, by atoms or whatever, it behaves like a particle. And that is a bizarre contradiction. And I personally think it's one of the coolest things in science. If you're waiting for me to give you a final answer to this as well, I'm going to spoil the surprise right now. We haven't figured this out. Okay? This has been a puzzle that's been around for 100 years, and some of the greatest minds ever, okay, have worked on this. We haven't figured it out. We don't understand how this is possible. There's some theories on the table. None of them, turns out, are testable, but it's just bizarre. And I'm just going to remind you that 20 years before they discovered any of this quantum stuff, the scientists were kind of like, sort of boldly predicting that all questions would be answered as soon as we had the model for the atom. Well, that turned out to be Pandora's box, right? You open up, that box, what the atom is, and it turns out that there's some strange things going on that no one could have ever guessed. That's why it's such a great story. Like, it's almost like we were a bit too naive, okay, saying that all questions would soon be answered. And that sentiment was soon destroyed. And it turns out that the universe is a far more bizarre and complicated place that even our best and greatest minds have a hard time imagining and understanding. Okay? So this is a strange, strange thing that's going on here. Now, I just want to tell you about something else. In case you're thinking that we figured everything else out, it's just light that's bizarre, you're wrong. Okay? So what happened is a few years later, when they're doing all these experiments, someone got the idea, well, what if we fire a beam of electrons? Now, electrons are particles, right? Case closed, they're particles. No one ever thought any differently than that. Okay? They had no reason to. But someone thought, hey, let's try this. If light behaves like a wave in the double slit experiment and behaves like a particle under other circumstances, why don't we try shooting a beam of particles through the double slits like electrons? Okay, so let's fire a beam of electrons through the double slit. The technology became available eventually, right, to do that. Someone tried it. I think you can guess what happened. They saw the interference fringes. So in other words, we're not just talking about the bizarre character of light with quantum physics. It turns out everything has this bizarre character, including the stuff that you and I are made of. In other words, matter. Both matter and energy behave in this bizarre dual nature where sometimes like waves, sometimes like particles. It makes no sense. Okay? Those two things, waves and particles, contradict each other. So like when you do the double slit experiment, if they're particles, there's no waves there. Like, when an electron goes through the double slit, where's the wave? Where's the crest? Where's the trough? There are no crests and troughs, but yet you get interference pattern. Okay? And when, light passes through the double slit, really you can think of them as photons, so they're particles, but again, where there are no crests and troughs there apparently, okay, in the quantum theory. But you still get the interference. So, guys, like, it is a bizarre universe that we live in. And I kind of find it comforting that we don't have all the answers. I think that they were quite naive back in the late 1800s, thinking that they would have everything figured out. They couldn't have been farther from the truth. Okay, and so let's just go through and see, now that the scientists have this puzzle, okay, this wave particle puzzle, now what? Okay, so anyway, I wrote some notes here. Okay, so here, in these two things here, number one, I'm going to highlight this for you. Number one, when we're trying to explain the double slit experiment, I'm going to use that as my example. Interference, diffraction, polarization, thin films, all that stuff that we did with wave theory and light. You have to use the wave theory to predict what's going to happen in those experiments. The quantum theory does not predict it. Okay? Like, it fails to predict what happens. And when a theory fails to predict, it has to be false. So in the wave experiments, the particle theory is just false under those experiments, right? Now, when you're looking at the photoelectric effect or black body radiation or the Compton effect, you have to use a particle theory to explain those, and the wave theory fails. And so in those experiments, the wave theory is false. So sometimes light is a wave, and sometimes it isn't. It just depends on what you're trying to do. Okay, if you put it through double slits, light just goes, all right, you're putting me through an interference thing, so I'll behave like a wave for you. But then when light is being absorbed and emitted by matter, it behaves like a particle. Okay, so scientists are completely baffled by this, and like there's some sort of like not so enthusiastic statements from the scientists saying, well, maybe light is a wave on 3 days of the week, and the other 3 days it's a particle, and then on Sunday it takes a break and it's neither one, right? And there's actual quotes from actual scientists like along those lines, okay? So in other words, this was completely baffled everyone at the time, okay? Now see, and I tried to underscore that for you here. Some students will think maybe there's a way to put those two theories together, right? Maybe we can come up with some type of wavicle, right? Where there's this weird thing out there that has a wave character to it, but it's also somehow a particle at the same time. Yeah, but you don't understand. Particles behave in a particular way, okay? And they just don't produce interference if there's nothing waving, right? So you might think, well, maybe there is something waving, okay? So sometimes scientists came up with this idea of something, and it sounds a lot like Christian Huygens' idea of the ether, but there's some type of mysterious medium out there, or whatever, that's piloting the particles in the double slit experiment. Okay, well, it didn't take long for them to falsify that idea. Okay, with experiments. Okay, now here's where it gets even stranger too. It's kind of cool. I was telling you here that these guys, Davison and Germer, fired a beam of electrons that produced an interference pattern. Okay, so we're not only talking about light. It's everything that has this bizarre character. And what they did was they said, all right, let's take a beam of electrons and let's fire them one at a time through the double slit. Okay, now when electrons, the way they did this experiment is electrons were fired through a double slit, and they would hit a screen, and the screen was a phosphor screen, sort of like those old television tubes. And when an electron hits a screen like that, a dot will glow. Okay, so when one electron got fired through, if it made it through the two slits, you'd see a dot glowing on the screen on the other side, right? Now, if you fire one through, you just see one dot. Two, you see two dots, and so on. And so what they did was, after like, tens of thousands of electrons have gone through, you see many dots have occurred on the screen. And when you look at all of those dots put together, you see the nodes and antinodes, right? And guys, like that is a very, very strange thing going on. Because think of it like this. If the electron is just this tiny little dot, okay? It's this tiny little particle. Logic says that it can only go through one of the slits. Does that make sense? But here's the deal. In the double slit experiment, the separation of the nodes is given by this equation. Now, here's the weird thing. If matter produces interference, you can find the wavelength of an electron, right? Because we can just do the experiment and measure delta X, L, and D and find the wavelength. Okay, so electrons have wavelength. So weird. Like, we don't even know what's waving. And you can do it with protons. It still works, no matter what you throw through there. Okay, so anyway, the point is, what if we change these variables? What if I change L? If I change L or change D, well, it'll change what delta X is, right? So, in other words, delta X is the spacing of the nodes and antinodes. So if you're looking at the screen as these dots are appearing, like if you're thinking, okay, the electron goes through one slit at a time and then just lands on the other side, but here's the thing, what's the probability of it landing on a node is 0. So it never lands on the nodes. It's as if it knows where not to land. Okay, now there's no obstacle that prevents it from landing on a node, like an interference pattern, that looks like this, right? And I'll just use dark bands for the nodes. It looks something like this with nodes and antinodes, okay? And then we said that this is delta X, right? The spacing between, let's say, two nodes. Well, why won't the electron land right there on that spot? Why won't it land there? It can't. Now, there's nothing preventing it from landing there. It's got a line of sight. Like, it's not like the slits are getting in the way and it just can't land there. No, like it's like me trying to throw the ball at the wall and, for some reason I can't hit this one spot. It's right in front of me. Can't hit it. See, the electrons seem to know where they're not allowed to land when they go through the double slit apparatus. Because if you change these two variables that I'm in a circle, then that spacing will change. And so they know what they know what L and D are. But electrons are just these dumb particles, right? How do they know anything? Like, they don't know how far the screen is away, okay? And they don't know how much the slits are separated. Like, let's say we were to blindfold you and we send you through a door. Would you know if there was a second door? If we bring you into a room and you've never seen it before, you're blindfolded, and you walk through one door, would you know about another door being there? Okay, well, the electrons, not only do they know how far away it is. They know its separation, because D is the separation of the slits, and that determines this spacing. They also know how wide the slits are, because there's a double slit pattern that will show up, or a single slit pattern that will show up too, that we've seen before. And so one electron that gets shot one at a time lands at the right spot. It seems like the only way to explain it, and there's a guy named Richard Feynman who explained it this way, who's a really brilliant quantum physicist. He goes, the only way to understand it is almost as if the electron took, that one single electron takes all possible paths all at the same time. So that's how it knows what D and L are, and that's how it knows where to land. So it's like, we have this expression, you can only be in one place at one time. We're not only saying that the electron's like in two places at once. We're saying it's like in an infinite number of places at the same time. Because how many possible paths are there through those slits? Well, there's really an infinite number. How many ways could you go through a door? Okay, well, I could sit on my chair for a while and go in 5 minutes, right? Or I could crawl through in 10 minutes, or I could sit here for 10 minutes and 0.001 seconds, and then I could jump through the door, and just if I change the amount of time, I could go through that door there's so many possibilities of what time and actions I could do before I went through the door, okay? Well, the same is true for the electrons. Some electrons go straight through. Some will maybe hit the edge and bounce through. Some will, maybe hit the ceiling and bounce through the slit. And when you think about how many possible paths there are for the electron to make it through the slit, there's actually an infinite number, okay? An infinite number of possible paths. You can't really count them all. You could always come up with another one. But the electron behaves as if it's taking them all at the same time until it hits the screen and it lands on one spot, then becomes sort of just one little guy again in one spot at one time. Right? So scientists are really smart. They said, all right, this is just too strange. We can't take this weird, spooky behavior. So what they did was they put a measuring device at each slit to measure when the electrons would actually go through, like which slit they actually went through, right? So we're going to peek, so we're going to peek at the electrons and we're going to see, all right, what slit are you going through? And what happened when they did that, guys, is that the electron actually stopped behaving like a wave. So if you peek and you watch it, it behaves normally like a particle. No more interference. You have to not watch it. Okay, so if you can't see it, if the information on which slit it goes through is not available to you because you never measured it, then it behaves like it's everywhere at once. Okay, and then when it hits the screen, it collapses down to one spot again. But it's weird. How could it be everywhere at once? Okay, and don't forget, you and I are made of this stuff. What does that mean for us? Okay, well, anyway, so that's the kind of thing about it. Now I want to show you some photos. Okay, so look, here are a few electrons. Okay, like let's say 1, 2, 3, 4, 5, 6, here 7 electrons have hit the screen going through the double slit. Now here we have hundreds, of electrons that have hit the screen. Here we see thousands. There doesn't seem to be a pattern at first. But after maybe hundreds of thousands, okay, like 10 to the 5 plus electrons here, we start very clearly seeing our nodes and antinodes forming, as if they know. And don't forget, like, we only looked at single and double slit interference, but there you could have 3 slits, 4 slits, 5 slits. The electrons will be affected by how many slits you have, and that will affect their spacing and their intensity and everything else. And so, how do they know? Like, a wave can go through 2 slits at once because it's not a localized phenomenon, but an electron is a dot, one spot at one time, right? How could it possibly do this? It's yeah, it's bizarre. There is no answer to that question, by the way. We don't know how it can do that. It just does, right? In other words, electrons behave like waves sometimes and particles sometimes. Now, electrons behave mostly like particles almost all the time. And sometimes they behave like waves. Light is kind of the opposite. Light behaves like waves most of the time, and sometimes in a few experiments behaves like particles. Okay, but still, they both have the same kind of character. They both have this dual nature. Okay. So anyway, I tried to explain it in the notes here. All that, I'm not going to read this to you now. Okay, so mathematically, the electron's not taking just 2 paths, but an infinite number of paths. This is baffling, right? And so anyway, the interference patterns disappears if you peak. Okay, if you place detectors on the slits, because the detectors disturb the electrons, you see. And that seems to have this effect of collapsing the wave character altogether whenever you peak. And by the way, you can do that with photons too. You can put a polarizer on each slit, and the polarizer will tell you, and you can reduce the intensity of the beam, so only one photon is going through at a time. It's so dim you can't see it, but you put a photographic plate which gets exposed when photons hit the plate. Okay, and when we develop the film, you'll see the interference pattern, but if you put polarizers on it so that you can tell which photon went through which slit, then what happens is you don't get interference anymore. So even electrons will do that too. You can't peak. They won't behave like waves if you peak. Okay. How strange is that, right? Anyway, it's almost like you have this amazing superpower where you could be everywhere at once, but the superpower is defeated if anyone watches you. Okay, if we watch you, you can't do it. Okay, you have to not be watched. And when you're not being watched, then you're everywhere at once. Okay, and then as soon as we turn to look at you, you're in one spot again. Now, how do I prove that that theory is true or false? Because like as soon as you try to measure it, it changes its character, and that's why these things like have proven like these theories and stuff very difficult to prove. Some of the interpretations of quantum physics. But anyway, I'm going to stop there now. I'll save. Actually, hang on. No, let me go through this part here. Yeah. Okay. So there's something called the de Broglie wavelength. So this is how you measure, remember how the momentum of a photon is P is equal to H over lambda? Well, the momentum of an electron is P is equal to mv. Okay, so it turns out that if you substitute in mv for the momentum of an electron or a particle of any kind, and then you solve it for wavelength, you get this equation here, and we call this the de Broglie wavelength, named after a scientist. It's really easy math. And here's the thing of a mass particle. Like an electron has real mass, right? So that's what you put in for m, the mass of the electron. So anyway, I wanted to show you something about Niels Bohr. Niels Bohr was the guy who did the atomic model, right? Like the Bohr model of the atom. Okay, and see, for proof that electrons are weird, the energy levels in the atom. Okay, so if you think of, like, for example, the 1s, 2s, 2p, 3s, 3p, these energy levels, okay, they all have particular shapes. And maybe I'll look at these shapes another day, okay, on the last lesson. But they all have particular shapes. Now, why do they have those shapes? Well, here's the thing. Electrons are not behaving like particles around the atom. They're behaving like waves. Okay? And these shapes are like harmonic modes. Okay, they're like harmonic modes. They actually have nodes and antinodes in them. Like p orbitals have very definite nodes, okay, where the electrons will never go. And it's kind of weird. Okay, but I think really cool. It's almost like it's like a musical instrument, the atom, and the electrons energy levels are like different harmonic modes on a, you know, of the electron. So it's like this wave interference pattern. That's why if I were to show you an example of, like, say for example, interference on the head of a drum, it's so cool. Okay, how much it resembles the shapes of these orbitals. Okay, so anyway, this is wave behavior. And that's why when you try to explain the orbitals as if electrons are little dots or little particles, it really makes no sense what's going on in there, right? So if we say, oh, well, the first orbit can only have 2 electrons, well, why? Okay, well, you can't answer that question. But the reason why it's so hard to answer that question when you're thinking of the electrons as particles is because they're not behaving like particles in that scenario. And that's why when you're trying to use a particle understanding to impose that understanding on the atom, you fail because the electrons are actually behaving like waves in there. And that's why there's no orbits in between 1s and 2s. Like an electron couldn't exist in between those two because you're just going from the first harmonic mode to the second one, and there's no harmonics in between. That's why they're quantized like that. Okay? Anyway, so that's it for today. I know it was another long one. There's not a lot of math, to be honest with you. If you look at the homework and the outline. All right, so we did some questions of the Compton effect. There's very little math there. And here the de Broglie wavelength questions, do those two. They don't take very long. Okay, they're just using the equations that I showed you there. The equations are like one step easy. Okay, so we're almost done, guys. Just basically one lesson left, and then we're going to finish off everything, have a test, and we're done. Okay, so by the way, I entered your report card marks, and I used whatever was better, pre-pandemic or currently what the mark is. Now we still have one more test, so there's your chance to improve. Most of you have gone up during the pandemic, so here's another chance for you. It's a pretty easy test. It's a lot of information, and since it's open book, it makes it easy. So, yeah, we'll leave it there for now, and we just got a couple things left. I like this, though, quantum weirdness. I mean, isn't it weird, my lesson today? I know I kind of rambled. You can't help but ramble with quantum physics, though. It's kind of a rambling topic, like where people don't make sense. If you're finding it confusing, join the club. Okay, I took 4 years of quantum mechanics in university, and at the end of it, the professor said, all right, raise your hand if you understand quantum physics. This is actually my 5th year at university because it was a 5-year program. So the very last class in the 5th year of university, the professor said, all right, who here understands quantum mechanics? No one raised their hand. And he goes, good, because I don't understand it either. Okay, now what we mean by that, of course, is there are lots of problems. Like, you'll be able to do the math that I've given you here, and so you can do the math. So, you know, you just plug numbers into the equation, but do you understand what's going on here? The answer is no. So we could all do the math. So, you know, if you want to build a device that works on quantum physics, well, we can all do the math, so we can build it. Okay, but we don't understand what's going on. And isn't that kind of what science is all about? It's trying to understand what's going on. Yeah, we're having a hard time with that one. So no one really understands it. That's the best I can do for you. Maybe it's unsatisfying. I'm unsatisfied by it too, but that's good. Okay, so maybe one of you will crack this open, find some new direction to go in that no one's ever thought of before. That's what it's going to take. Okay, because so far our theories on the table have not proven very good. All right, so we'll end this one for now, and we'll talk again tomorrow.